Hello, this is Reena, and today I'm going to talk about our project where we were asked to select a well from three well locations where a private supply company is trying to develop a groundwater resources in Jefferson County. It has a goal of creating a water supply sufficient for 30,000 municipal consumers. We are supposed to select a location and create a wellhead study a wellhead protection area around it, and also create a capture zone analysis. Our wellhead protection area is an area around groundwater well where activities and land uses are regulated to um, protect quality of groundwater resources so that it is ready to supply to the consumers. So for this our starting assumptions, like we had three well locations with its latitude and longitude in degrees, and our number of consumers were 30,000. And from the uh, from for Texas, since the water consumption rate was 92 gallons per person per day, our pumping rate was around 2.76 into 10 to the power 6 gallons per day. Since we were supposed to take a negligible amount of drawdown, we took our drawdown to be 5 feet. For storage coefficient, we looked into some reports of lower Chukat aquifer and upper Chukat aquifer. Our well A fall in the upper Chukat aquifer region, so we selected its storage coefficient according to the upper Chukat aquifer, which was 0.0002, and for well B and well C, it fell in the lower Chukat aquifer region, so the storage coefficient was taken as 0.063. Accordingly, for transmissivity, we had the TWDV report 98B for different well locations for a different county in Texas. So for Jefferson County, we got 10 well locations which had different transmissibility for different locations. So for those locations, we created a Voronoi polygon, and after creating a Voronoi polygon, we checked in which Voronoi region our Voronoi polygon are well falls, and according to that we took the transmissivity for our wells. So after transmissivity was taken, we then used the Thies solution, which is an analytic solution for calculating drawdown in unconfined aquifers due to constant rate of pumping well. So according the Thies solution was derived by Thies in 1935, and he assumed his assumptions were that the aquifer is homogeneous and isotropic. The aquifer has the infinite areal extent. Its discharge well penetrates and receives water from entire thickness of the aquifer. The aquifer we are studying is Gulf Coast aquifer. The cost coefficient of transmissibility will be constant at all times at all the places. The well is supposed to have an infinitesimal diameter, and the final assumption is that water removed from storage is discharged instantaneously with a decline in head. The formula for this solution is given like this, where S is the drawdown in feet, Q is our pumping rate, uh, T is the transmissibility, which is a measure of ability of aquifer to transfer water and study how well water can move through aquifer. It's in gallons per day per feet. And then U is a dimensionless parameter related to time and distance. WU is the well function, which is directly related to U. R is our radius. S is the storage coefficient, which is the ability of aquifer to store and release water, and the small t is our elapsed pumping time for the well. So by taking this, we had our drawdown, pumping rate, transmissivity, storage, and so by doing the further calculation, we got our radius for different years, 2 years, 5 years, 10 years, and 30 years for three wells. Then for those radius, we plotted the buffer zone, the zone it covers in the using the QGIS software, and the different buffer zones for well A, well B, and well C can be seen here. As we can see, well B has large area of buffer zone. Well B has um, slightly lesser area, and USA has a less area. So by looking at the area it covers, we preferred we'll see as a well. But to further study in the area, we used the LOLC, latest LOLC data, and clipped it to the buffer zone of 30 years for all the three wells. While looking at the LOLC data, we can see that the comparing well C and well B, we can see the well B has larger urban area as compared to well A, well C, and we can say that well C is better as compared to well B. Also, we also looked at the toxic release inventory, and the toxic release inventory count in each well were for well A it was 106,000, for well B it was 2,000, and well C it was 1,000. So by looking at all the parameters, we ranked our wells as our first ranking was given to well C, second was given to well B, and the third ranking was given to well A, for these locations and our calculations. Thank you.
Hello everyone, I'm Dr. Srishta, and I'll be continuing the second part of capture zone analysis. So for this, first of all, the water elevation values are taken from groundwater database obtained from Texas Water Board, Groundwater Board. So for this, this is done for to determine the regional groundwater flow, and the counties taken are Orange, Jefferson, Liberty, Chambers, and Harding, etc. So now the often groundwater water elevation is converted into meter, and then this is imported into GIS to GIS, and the 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 data is reprojected to Olbers conical equals area, and then in attribute area the easting and northing is calculated so that we can do the calculation in meter, and the value obtained value is accurate. So these are the points that we got for um, water the water elevation got for water elevation for different counties, which are at the regional area of Jefferson County. So the as we have taken the well C as the pumping well that we are going to take for this this project. So these are the values. So next, now we are going to use the equation to fit the model. The the equation that we are going to use is ax plus by plus c equals to h. So for a and x and y are the spatial location of those water elevation, and h is the groundwater water elevation. So from here we need to find out the AV and C, the coefficient of normal vectors of plane. This is determined. So to find out the capture zone orientation, and H is the actual height height of the groundwater elevation. To do that, we need to fit the model by using linear regression model. For linear regression model, we are going to take we are going to create the model, and then we are going to fit it so that we can get the values of A, B. So from here we have gotten that the value of A is minus 0.000146, and the value of B is 0.00044. Now, for the capture zone analysis, with the assumptions that we are going to make is that the location of the well is at the point 0, 0. That means the well act as a center of the center, and the x coordinate axis is parallel to the regional direction of the groundwater flow. So the x coordinate is parallel to the flow. And now we are gonna find out the groundwater gradient, which is dH by dr. This is found out by taking the square root of a square plus b square, the values that we found out before, and then for the angle, it is arctan b by a. Now we need to find the relationship between the various coordinates of x and y of capture zone. For that, since we are going to select, since we selected well C, the value of regional groundwater flow is found out by multiplying transmissibility with the groundwater gradient. So stagnation point, it is the point where the water doesn't move in any direction. It is where the point where the water remains stable, and so this is found out by taking the formula QW by 2pi Q naught, and for that place y stag is taken is 0. The dividing point along the y axis uh, is the uh, maximum y y of the catchment zone. So for determining the x and y values, we are gonna use Python code. So for this, for finding out the capture zone boundary, first of all, we're gonna take the constant values of x stag, y division, q naught, and qw. We're also gonna take the pumping well, easting, and northing. For calculating the x and y coordinates, we will take the values of y coordinates from minus y division to plus y division by 2, and we will take 200 values, random values. So after that, by using formula, we are going to obtain the x values. So after that, next is the for the values of x and y, the center of the well C, easting and northing of center of the well C is 88, so that we can get the actual spatial location of the capture zone. So next we are going to find out the capture zone after the rotation. So why do we do this? So we do this to ensure that the groundwater is captured effectively, and the capture zone is for that the capture zone is rotated by angle, and that we obtained before by fitting the model, which is 18.39 degrees. So for rotating the catchment capture zone, we are going to take the rotational angle in radian, and this is the formula that we take so that we can rotate the parabola by from its axis, from its center x-axis, and after that we are gonna add it with the center of the well C, and get the spatial location of the rotated coordinates. So for the capture zone image, this is the capture zone image that we got. The green one is the rotated capture zone, and brown one is the one that we obtained before. So these are the differences. Thank you.